So, but basically, so far, what we have covered so far, and in fact, a lot of what you learn when you learn programming and algorithms and stuff like that, they focus on the program. It's like the program is the most important thing, right? We take a long time to make sure that the program has no errors, and its programs tend to be very large, and there's all sorts of things about the program being the central focus of attention of programmers. But there's a whole other side to programming that's actually the focus is not necessarily the programs, but the focus is the data, right? And the data is perhaps the most important thing of what is going on. And the programs are either, you know, transient little scripts that you write and then you throw them away. You don't even put them on source control. Or they are not transient, they're more permanent, but they're not that big. They tend to do something that basically the most of your work is focused on the data and making sure that the data is stored appropriately and it's backed up appropriately, and that you can query it in the ways that is appropriate for your situation. So data-centric programming, as I said, is a collection of different kinds of styles that where the data is the most important thing, right? And the focus is on the data and not necessarily on the programs. So to that extent, I'm going to talk about these three things this week. I'm going to talk about SQL, and I'm going to talk about data flow in terms of reactive programming, which is the model behind, for example, Excel. And then on Thursday, I'll talk about the real data flow, which is, the concepts that give rise to the streaming APIs, and a lot of other things of that sort. So I'll just talk a little bit about SQL. I have a bunch of slides about SQL, but I don't want to spend a lot of time. Also because this year I decided that you're not doing the SQL homework anyway. But so that you know, the idea, I'll just tell you a little bit. I'm not even going to talk about this. Let me see if I have just the bottom line and what I want to talk about. So the idea behind SQL is actually quite interesting. So from a history perspective, SQL was invented in 1970, in the late 60s, and there was a paper in the 1970 by Cod, who worked at IBM at the time. And so what you have to know is that there was we're talking about mainframes. Okay, so this is the time of mainframes, and big banks of data that needed to be stored and queried for transaction processing and things like that. This is before the personal computer, and so there was a lot of technical discussion about what was the best way of storing the data, because it seemed that really the data at the time was really some of the most important things. So the companies that use computers, they used computers to process the data, right? So these were big banks, the big labs that did projections of satellites and things like that. So this was data was really important, and there was a lot of discussion about what's the best way to store the data. Also coming from the fact that up to before the up until the mid 60s, the way that you stored data on secondary storage was with the tapes, right? So I don't know if you guys, I don't have a tape here, but I don't know if you guys remember the tapes, the physical tapes that, in order to access the data, you actually have to rotate the tape one way or another. So it was kind of slow to access the data. Only in the mid 60s, there was the new technology of direct access storage, what's known as hard drive, with the disk these days, and where you have a head that can jump to any point of the disk, right? And that made the access much, much faster than sequential access through the tape. And so it made it other, the question about what's the best way of storing the data also depends on how, the physical storage technology that you are using. The best way to access data in a sequential tape is not going to be the same as the best way to access the data in a disk where you can jump around. So the relational model came very much on the heels of the direct access storage technology, where you can, jump around. And so it's based on something that's very mathematical. Again, this comes functional programming. It's not actually, it's more generic than functional programming, as you will see. It's basically relational model. Relational model comes from basically relation as in mathematics. It's a set of data that relates to a set of other data, and the difference between a function and a relation, if you remember from mathematics, is that a function is a relation. So a relation can be more than a function. So a function is a relation, a particular relation, where the same input cannot map to two outputs. So if you give it one input, it has to have one output, right? And two different inputs can map to the same output, but the same input cannot have two outputs, right? That's not a function. A function cannot have, for each input that you give it, it cannot have two inputs. Outputs can only have one. A relation, however, does not have that constraint. So, for example, in here, you see that the number -2 relates to 3, and it also relates to 0, and that's perfectly fine. It's a relation. This is not a function. So you would not be able to define a function that has this behavior. Okay. This is a relation on the left. This is a relation and a function. It just, all of the inputs happen to map to the same output, and that's okay. That's a function. It's also a relation, right? So relation is basically tuples of things that exist together. That's what a relation is. And so that's where the tables come from, right? It's the tables of the SQL come from. It's basically relations, tuples of things that relate together. So I'm going to skip through all of this stuff of SQL, and just to tell you that the important thing about SQL, if you read the code paper that I have linked from the page, it's actually a very interesting paper, very, very accessible. It's very accessible, and you will see where the mathematics of SQL comes from. It comes from relations. And so what can you do on relations? You can permutate them. So basically, interchanging columns yields the converse relations. You can subset them. So you have a relation is basically a set. You can subset it. You can project. Basically, you have a relation with many dimensions. You can just project that relation on a subset of dimensions, and then you get another kind of relation. You can join. So if you have two relations, and if they happen to have some of the fields that are the same, then you can join them, which is basically some sort of a cross product, some variation of a cross product between the two relations. And so all of the things that you do in SQL, like for example, select, the select statement, where, with a where clause, this is essentially a subsetting. Right? You have a big relation table, and now you're getting only the rows that have properties, right? So you have that you're subsetting. So the select statement like this is with a where clause. It's basically the subsetting operation. Where did it go? A select statement like this, where you also specify what columns you are interested, then this is both a subsetting operation because it has the where clause, but it's also a projection. Okay, so you're basically saying what the dimensions that you want to have that you want to look at. So this is a projection. So basically, and the joins, the things that you do in SQL, which are joining tables, is basically the joining relations. It's it comes from, it existed before, well before SQL. It comes from mathematics, at least 2 centuries ago. So all of the ideas that are in SQL come from mathematics of 2 centuries ago. That's just so that you know. And it's stuff that we will learn in high school, with sets and subsets and kinds of operations that you do on sets and subsets. So this is what I wanted to talk about. But in terms of the programming model that is kind of suggested by SQL, what we have here, when you have an application that is backed up by a database, typically the storing of the data is very important. And another thing that's very important is accessing the data. So accessing the data based on perhaps unexpected ways that we might not even predict a priori, right? So if we knew exactly all of the things that we want to extract from the data, then maybe we wouldn't need something as sophisticated as SQL. But the idea is that we want to store the data so that we can change our minds about what kind of operations we want to do on that data later on, right? So that's why SQL as a language is very powerful, because it allows us to basically declaratively explore the data. We can select something from the tables right now, but then as the application evolves, we may need another SQL statement, and it's very easy to write another SQL statement. So SQL statements are very powerful and flexible ways of basically doing different cuts at the data whenever we need to do those different cuts at the data. So, but a lot of thought is required in order to store the data in ways that are going to help us change our minds in the future. So what kinds of tables we want, how do we want to relate the tables, the foreign keys and all that stuff. So all of that needs to be thought a priori and designed a priori, so that later on we can access the data in ways that we may not even think in the beginning. Okay, so a lot of the programming cycles in this world are spent on actually modeling the data, right? And then the little SQL statements are, as I said, sometimes they are transient. You just want to write a little SQL statement, you get a piece of the data and just throw the SQL statement away, right? So that's one data-centric kind of programming. So another one that I want to talk about is the one that you have your homework on, is these days this is actually have a name. It's called reactive programming. Okay, and reactive programming is basically the model of spreadsheets. And I have some spreadsheet open here. Do I have a spreadsheet? I had a spreadsheet somewhere. Let me see if I have a spreadsheet here. Let's see, I had a spreadsheet here. Grants. Maybe this one. Okay, this one is not a good example. Anyway, I trust that everybody knows, has used spreadsheets before. And the interesting thing about spreadsheets is that so again, it's one of the most successful software genres out there. It was perhaps one of the first kind of personal computing applications that came up in the era of personal computers. But it's based on centuries-old accounting practices. That's the important thing. I mean, the idea of spreadsheets comes from accounting, from the balancing the books. And some cell in which even in those books, people already knew and had that practice, that some columns contain primitive data, data that you have to put, and other columns are data that is derived from operations on primitive data, right? So you have the individual items, prices, and whatever, and then you have a total, right? That is the sum of the individual items. And so that was already there for a very long time. But basically, when computers came around, there was this idea, okay, so can we basically make a computerized version of this idea that has been around for a very long time? And that's data flow programming comes from not only from here, but this is an example of data flow programming. And the idea behind data flow, actually the reactive programming in this particular case of spreadsheets, is that you have a program, quote, you have some program which is represented at any point in time by a rendering of the data. Okay, so you are rendering some data on the screen or whatever, right? But behind the data there is a program. And so when you change something in that data, okay, there is an immediate reaction that happens that certain other cells that depend on the value that you changed are going to be automatically updated. And so they are going to react to the input. So basically there's sort of a skeleton. Okay, so you see, what you see is the rendering of the data, but there's a skeleton behind the data. And that skeleton has constraints on the values of what you see on the data, right? Which is the formulas or whatever, some constraints. And so when you change something on the data that you see, then that machinery, underneath machinery, kind of reacts and updates what you are going to see with the new values and stuff like that. That's sort of reactive programming. Reactive programming is an example of data flow. So let me explain to you how to do term frequency in reactive programming style. And I think this is, yeah, this is all. I don't know if you can read this. I think I'm going to show you this in GitHub instead. So here's so here's the exercise. Even before I show you the example, think for a bit. How would you do term frequency? The problem that we've been working on. How would you do it in Excel? I want some, if you have some ideas, please unmute yourself. How would you do this in Excel? Let me start in Excel here.
I mean, maybe you would like import the data, like import all the words into an Excel.
Yeah.
And then somehow you would have to count it from there. I'm trying to think.
Right. So I have just an example just so to get your juices flowing. Here's a spreadsheet. So I'll put all like a column called words, and I will put the words here, right? It is a truth. I'm sorry, a truth of universal, whatever, right? So I'll put the words over here. And then what? What else would I need to do? Yeah, so count and count if. All right, so we could do that. So Simon is suggesting to count. We definitely need to count. First, we need to eliminate the stop words, remember? So we probably will have another column for the stop words. Okay, so here, all the single character things plus things like 2, 4, I don't remember the stop words anymore, the whatever, okay? So she, yeah, whatever. And then and now this is going to be our input data. This is all the input data that we need. From here on, all the other columns are going to be data that is going to be derived from this input data. So here, perhaps we're going to have the words that are not stop words, maybe. Let me see how I solve this. Here. Right, so the unique keywords, that's right, that's my third column. Okay, now I lost my table. Where'd my table go? Here. So unique words. So basically this would be, you know, the formula here would be something like this. If this word is not, if this word is not in column B, then it moves here. If this word is in, for example, A, so for example here, A. So A is in column B, then this is going to be blank. I don't know if it is does anybody remember if it is a stop word? Maybe it is. Let's say let's say that it is a stop word and that is also a stop word. Okay, so in this case, this would be blank, this would be blank, this would be blank, this would not be blank. Truth. I think of is also a stop word, pretty sure. This would be blank. Universal, right? So the column C would be the column of unique words, right? The words that are not in stop words. And from here on, now we can count stuff, right? So now we're going to count. So the other column, let me put this tab closer to here. My other column is going to be the counts, right? So this column is going to be the counts. So, and it's going to be something like, you know, the first one, it's going to be for the first, the truth, for example, I don't know, it would be whatever, 45, I don't know. So basically the same sequence would be the same sequence of words that appear here, you know, etc. Universal would be, you know, whatever, 50, I don't know. So there's some formula here that counts the occurrence of every single word in the unique words. And then we have to sort, right? I'm sorry, this is not what I want. We have to sort the sorted data. So now another formula over here, sorted, that is going to take the unique words over here and it's going to sort them. And maybe it's going to take the unique words and the counts and it's going to sort them. Right? And then finally, at the end, we're going to have counts and you know, we can say the 25 top most are going to be the first 25 over here. So basically, this is an interesting exercise that I actually, if you want, try to figure out how to do term frequency in purely in Excel formulas, because it's possible. So what I have in the exercise is not Excel, but it's a programmatic version of Excel. So if you see, I'm going to model Excel as a series of columns. Okay, so what you see here are the columns. So I have 1, 2, 3, 4, 5 columns, which are the ones that I just typed in there. And what is a column? So now we have to think a little bit about what is a column. So basically, a column is two things, and this is an important thing in reactive programming. So what it's basically two things: is what we see. So it's a rendered data, which is going to be the first first element of this pair, and it's potentially a formula, right? It could have a formula too. So for example, the two first columns don't have formulas because they're input data. So they're going to only have the data. But the other columns, they all have formulas behind it, right? So here are the formulas, and now you may want to, you know, search just lambda expressions that do what they need to do. You have to kind of read through them to understand, but basically these are the formulas that are going to fill out the data on the first part of this tuple. Okay. And so here the entire spreadsheet is all these columns, 1, 2, 3, 4, 5, and then the sorted data, 6, 1, 2, 3, 4, 5, 6, that's right. And so what is the program? So the program is very simple. It you know, gets all, you know, it puts all the old words on the first column, right? On all words. It puts the stop words on the second column, all right? And now it just calls update. All right, and the update is a function here that the only it's very simple. It just goes and traverses left to right, top to bottom, right, and runs the formula on every piece of data that you have. Basically, it applies in all the columns. For every column, if there is a formula there, then it applies that formula, which is a function, to and the result of applying that function is going to be put on the rendering part of that column. Right? That is the thing that we see. Okay, so and then you display it at the end. Now your exercise is two things: is to rewrite this in whatever language you want, but the second thing is to make it really interactive in your case. Okay, so we're going to put this update on a loop that asks for a user for a file name, and then when the user inputs a file name, then you update. You basically you can either do it in two ways. You can either reload everything again. You discard what was there and reload from the file, or you add to what was there. So you read a file, you had some values on these columns, and then you read another file and you basically add more words to the first column, and then you run update, and the counts and all that stuff are going to update, just like an Excel, right? If you added more columns, then the other columns would update automatically. So basically, the update runs on an interactive loop that asks the user for new files to process. Okay, so that's the reactive part. The reactive part, you can do it with this, like underneath this little loop, this update function. But the model is very simple. Is that the fact that you associate formulas, functions, with specific cells, right? With cells on a table, or could be on a graph. That's other models too. And then the reactive part has to do with when you update some of these cells, then there is the update function that runs and updates everything that depends on that cell. Okay, and that's basically what Excel is doing. Excel probably does something smarter than running up these functions on every single cell. Okay, it probably optimizes it. It knows exactly which cells depends on which other cells. But this is a simple version of Excel. Okay, any questions? Haha. Okay, I'm still trying to understand what the lambda function of the counts list actually does. Okay, this one is a mind shifter here. So here's what it's going to do. So it's a function that takes. I always take a long time to remind myself what is it that I wrote. It's one of those things that it's easier to write, but then trying to remember what it does is another thing. But so the counts depend on unique words, right? And it's going to, you see, non-stop words of 0. What is a non-stop word? Oh yeah, all right. Okay, no, okay, I got it. So non-stop words is different than unique words. That's right. That's right. Okay, that's the difference. So non-stop words is the column. Okay, this is an important thing. Non-stop words is this one. Sorry, there's a column that I should put here. Very important. Non-stop words. Okay, so this is going to be. This is going to be, this is going to be this. So for example, if I had another truth here, all right? So this was going to be truth. This is going to be universal. And this is going to be truth again. Okay. Actually, it's, I'm doing this wrong. This should actually be all flushed up here. Truth, universal, truth. Oh, what did I just do? Okay. All right, and this should be, I need to do this right. This should be unique words is truth and universal, right? So now I don't repeat. So column D is a helper function that tells me the non-repeated unique words without repetitions. So the column C has repetitions. Column D does not have repetitions. Okay. So that's an important thing to have in mind. So what I'm going to do to count is that I'm going to traverse the unique words. So I'm going to traverse column D. This is the one that I'm going to traverse. And then for each of the words on this column D, I'm going to count how many times it occurs on column C. Okay? So this is an important step that I had skipped. So basically the formulas that you see that looks very confusing, it's basically, so for repeat non-stop words of 0, try to remember what this does. Okay, so this is the lambda. Sorry, I'm taking time because it always takes me time to remember what is. I should probably write this down somewhere. The word at index of non-stop words list corresponds to its total counts in the same index in the counts list. Yes, I think there's something like this. So let me see. So map. So the map function maps a lambda, which is this lambda. So this is another important thing, is to parse what's going on in here. Okay, this is another important thing. So the map function maps a function to some arguments. Okay, so the function of this map is just this thing that I have highlighted. Okay, it's a function of 2 arguments. It takes a word and the word list. Okay, and it counts the occurrences of the word on that word list. Okay, so this is the function that I'm mapping. I'm mapping it to what? Okay, so I'm mapping it to the unique words. Okay, the list of unique words and the word list. So what is going to be my word list? My word list is going to be a repetition of the non-stop words I forget what yes, forget what this repeat is doing. This is the part that I need to Google. I don't remember anymore what repeat does. Does anybody remember what the repeat function does in Python? I have a very short memory. I only remember things and I'm actually doing them and I forget. It's very bad. So I'll have to Google what does this do. Python iter tools repeat. So we give the data and give it the number, how many times the data will be repeated. Okay. So we're repeating it the number of unique words. Ah, yes, right. Okay, I know what I'm doing. Okay, I know what I'm doing. All right. Because this is a map, okay, it's always, I always have to remember what I did. So because this is a map function, I need to give it all of the data that this this mapping is going to work on. Okay, so basically for each unique word, I need to generate the list of non-stop words, a different list of non-stop words. I have to create a different list of non-stop words for the map to work. Okay, so I have I have, my first unique word, for example, truth or whatever, and now I'm going to map this function on truth and the list of non-stop words, right? The list of duplicates. And then for another one, the universal, okay? I have the universal word, and I'm going to map this function here with the word universal, and again another instance of the list of all the duplicates, okay? So I'm basically creating, I'm shaping the data so that the map function works. And why am I doing this? You may ask. Because it might seem that you can do something much simpler with just a normal loop, for loop or something like that. The problem is that for loops are imperative, and you cannot have imperative code in these pure functions, right? So pure functions, I'm using pure functions here, right? It's lambda and maps and stuff like that. So that, which is great. It can be just a pure function, but the drawback is that I have to replicate the data every time. I cannot have a loop that would go iterate again through the same list of words. If you understand what I mean, okay? So the key here is to understand what this map is mapping. Okay, it's mapping each of the words in the unique list to the repetition, the list of repeated words, but it has to generate a list of repeated words for every single unique word. Okay, so this is what this is doing here. You can try to find, yeah. So another question, since you don't have a map operator in C++, it's okay to define this function outside instead of defining lambdas. Yes, you can do that. You can define a function outside and then call that function, by with have a function pointer or some sort of a higher order function that by name calls that the function that you defined outside. You can do that too.